So today we continue our talk about machine arithmetics, and last time we have said that when computer operates even on simple numbers, there arise a number of challenges that we need to overcome. First of all, as we said, even when we represent our numbers in binary, for example, like this one in here, this number can be first negative, then it can have a decimal point, so the number can become fractional. And although the digits are just zeros and ones here in binary, those digits are easy to represent in the computer because 0 would be electricity turned off and 1 would be electricity turned on. But we had a big problem what to do with a minus and a dot. We can't have other options for turning on and off electricity, just two options are available. So all information in our number must be somehow represented with zeros and ones. That was actually the first challenge. The next challenge is that our encoding, that representing the number with just zeros and ones, must be quite tricky because it must allow us to do all the operations like plus, minus, multiply, and divide very easy, and those operations must work same both for the fractional and integer, negative and positive, all different options that we can have here. So actually that was the second challenge, how to make this encoding efficient to express all operations with very simple algorithms. And the next challenge was the limited length. In the computer we always have a limited length for representing our numbers. We cannot have infinite amount of memory. Usually for a number we have just fixed number of bits. Usually it is either 8 or 16 or 32 or 64. Those are the options available in modern computers. And all numbers must be stored in this length of bits. So when you have a maximal number that can be stored in this particular length, and you try to add one bit, one more, you will start having issues like you cannot put bigger number here. In the result you will have the so-called overflow, the biggest and the largest bit, and all other bits will just be 0, as we have shown before. And in reality this overflow bit is lost. What remains is just 0. So our representation must be somehow proof to these overflows, so they will not be so critical. Okay. And finally, the final challenge that we need to address today is the need to represent very big and very small numbers. Actually, this is an example of very big, and this is an example of very small. And if you look at this number in which we have a very big and very small, we have many decimal positions in it. Here is the big part, and here is the small part. And to store all of this information, we must have very long representation. And this must somehow be consistent with the limited length of our representation that we have, in which we simply do not have place to store all these zeros in between. But still, somehow we need to store the value of this number. Okay, so these are the challenges, and today we're gonna find the solution for all of them, which is called the floating point arithmetics. So the topic for today is floating point arithmetics. For the students who have just joined us, I will repeat one more time that I highly encourage you to take notes while we have our lectures. That would be the easiest way for you to learn and just to remember. So, floating point arithmetics. In it, we will first discuss the exponential notation, which probably you have talked about at school, but we need to use it, so we will make sure that we really understand what it is. Next, we'll talk about the floating point machine representation, its precision, range, and special values. And we'll discuss the modern standards that are used in programming, for example, concerning this floating point arithmetics. And finally, how actually operations are done on these numbers. This will cover the rest of task 2 of your home tasks. So first, subtopic for today is exponential notation. What it is actually a way, a technology of representing real numbers. And actually, this particular way is used in all of modern computing. So exponential notation is a way of presenting real numbers. Real numbers are like, I know, 223.01. Yeah? They can be fractional or whole. They can be negative and positive. So, what this exponential notation is about? In it, any number x is represented by such formula. First we have -1 for the possibility to make our number positive or negative, and this -1 will be power s. So we have first parameter s. Next, continue. We have multiply. Next part of our number, in which we have 2 power exponent, some number that we will call exponent, and the last part is called, often is called fraction, or it has different names, but for now let's call it fraction. Let's give the definitions for these parts and give an example. So any number is represented with this formula. In this formula, the parts that we use here are called respectively as value S is called a sign value. The E value, next parameter, is called the exponent. And finally, the F number is called the fraction. Or it also has different names in different sources, in different literature. You can see it called differently. For example, it is often called significant. Or the same thing is often called mantissa.
Sorry, sir. The minus 1 power S is called what?
The S value. This S value is called the sign value. The E value is called the exponent, and the F value is called the fraction or significant or mantissa, which all are the same thing. We will use one of these names. Okay, so let's consider what how each of these three values really affect the x. First, the sign. The sign is the easiest. The sign can be just 0 or 1. This S value can be 0 or 1. If the sign is 0, in this first part we obtain minus 1 power 0. And of course, any value power 0 is equal to just 1. So, if sign is 0, this part can be erased. It is not meaningful. It doesn't change the value of our number. Multiplying by 1 changes nothing. Okay, if our sign value is 1 instead of 0, we have minus 1 power 1, and any number in power 1 is same, as it was before. So this part is equal to minus 1 then. So in this case, if the sign is 0, our number is positive. If the sign is 1, our number is negative. That is why this value S is called sign. It defines positive or negative.
Can you please say that again?
Okay. This S is called sign, and it can have two values, 0 and 1, right? If S is 0, our number is positive. In case S equal 1, the number is negative. Why? Well, because minus 1 power 0 is plus 1, minus 1 power 1 is minus 1. So that is about sign. Next, the exponent.
Okay, sorry please. Just to be clear, if the sign is 0, we get positive.
Yeah.
And if the sign is 1, we get negative.
Yes, right. Okay. And of course, I encourage you to just re-ask if you have doubts whether you understand it correctly. You are encouraged to ask. Okay. So the next part, the exponent. Well, exponent is just a power, a different fancy word for the power. Actually, what we have here is 2 power e, nothing more. So this exponent defines the magnitude of our magnitude of x. The bigger the power, our x is bigger, of course. Okay, and finally the fraction is a simple number between between 0 and 1. 1 is not including. Or between 1 and 2. We will discuss why two options are possible here, but in general, this number f is just a simple number either between 0 and 1 or between 1 and 2. Okay. Actually, if this number f is in the first range, 0, 1, our x is called denormalized. And in this case, if the fraction is in range from 1 to 2, the number is called normalized. And this second case is the default. It is the most used. Okay. So once more, in our notation for the exponent notation, the number is split into 3 different values. They are combined by the formula. The sign, which defines whether the value will be positive or negative. The exponent, which actually influences the magnitude. The bigger the exponent, the larger the number we get. And finally, the fraction, or significant, or mantissa, which is a simple number in the very narrow range, either normalized or denormalized. And normalized is the default. We will see why now. Actually, to see why, we must have an example. Let's have an example, some number x, which is minus 1 power 1. I will use such notation for power just to make it shorter in writing. Multiply by 2 power 3, multiply by fraction, which is 0, or let it be 1, 0, 1. And of course, all of our numbers are in base 2, because we are going to use them in computing in our machine. So this number is base 2. Well, this number we have written in base 10, but if we need to store it, it will also need to be stored in base 2. So, but for our example, let's put all numbers in base 10 just for this simple example. So we have a fraction in base 10 and the exponent also in base 10. And what it gives us, which number do we obtain? Here we can make it very easy. Minus 1 power 1 is just minus 1, right? 2 power 3 will give us 8, and 8 multiplied by 1.5 will give us minus 12. And that is just the representation of number 12. And in this representation, we need to note very important things. First, in our exponential representation, the number is fractional. So this last part, fraction, it is fractional. But it still can give us the whole number in result. Why? Because of this power, because it is multiplied by this exponent. And in this multiplication, the number may become integer. Okay. The next thing that we need to observe here, let's consider another example. Let's call it x1, and we will have x2. x2 will have a similar representation, minus 1 power 1 multiplied by 2 power 4, for example, and here we will have 0.75. So the fractional part, the fraction part is such, exponent part is such, and this number is exactly 12 also. If you calculate 2 power 4 multiply 0.75, you obtain again 12. And minus comes from here as before. In this example, we see that the same number, in this case minus 12, has two different representations. But those representations are not unique. You can have other representations also. For example, you can have x3 equal to, just copy and change a bit. For example, the power will be 2 and the fraction will be 3, and the result would be same. Actually, what we do, we change the power and we change the fraction respectively, obtain the same value. So what we note here, that the our exponential notation is not unique. That is very important. This notation is not unique, and each number has infinite number of ways of representing it. Okay, and this is bad. This is a bad news for computing, because in a computer we must have some specific, precise and unique representation for each number. Okay, so actually this poses a problem. The problem is the presentation is not unique. The solution for this problem is called normalization, like this. And that is actually the word that we had here already. The normalization is a simple rule that says that the fraction, this f value, last one, must be in range from 1 to let's do it like this, from 1 to 2. So we narrow the range in which this f value can vary. How does it influence our problem? Actually, if you look at these different representations of 12, you will see that only one of these examples really matches this rule? Only one, the first one, right? Here the fraction is lower than 1, here it is bigger than 2. And actually this normalization guarantees unique representation. Okay, and finally let's consider why it really guarantees a unique representation. Well, because if you change your exponent just by 1, your fraction should change 2 times by factor 2, right? Exponent is changed by 1, the fraction must change by factor 2, very easy, to give you the same result. But if you change any number from this range by factor 2, you obtain the number not in this range. Yeah? If you multiply by 2, you obtain the number bigger than 2, not in this range. If you divide by 2, you obtain the number less than 1, also not in this range. Okay? So normalization guarantees unique representation. Why? Because fraction multiplied by 2 and fraction divided by 2 both are not in range from 1 to 2. Okay. So there is only one representation that matches the requirement for normalization, in this case this one, and that is all that we're gonna need from usual math for our floating point arithmetics. Just this exponential representation. So now it's time for floating point actually to see what floating point representation really is. So the floating point representation is the next topic. Okay, we start from our formula that we had before. We will use it and put it here. In machine representation of real numbers, first the exponential notation is used. Exponential notation is used. It is the base on which this floating point representation is built upon. Okay. Next. Next step. In the machine representation, all the information must be stored in binary in our register. So the values for S, for E and F are stored in binary all together in one cell of memory. So, to represent once more, S, E, and F are stored in binary and are all stored together in one cell of memory. Actually, if we talk about floating point number, it always consists of these 3 parts, which are stored together. We will see now how exactly, but still. But before, we must consider how exactly they are stored. S is just 0 or 1. It is stored directly, represented directly. Okay. Exponent and fraction are a bit more complicated. Exponent is stored in biased form, so-called biased form. We'll not now give the definition what it is. Actually, biased is just having some bias. Yeah. What is stored is actually biased exponent. I will mark it as modified e, right? And it will be actual exponent plus some bias, which I will call E0, where E0 is called the bias. So exponent is stored in biased form, and this bias is selected such that for any exponent, any possible exponent, the modified exponent will be greater than 0. So we will not gonna need to store negative numbers in exponent, because we add a bias to them which makes them all positive. We will now have a look how it works, of course, but first let's finish this and talk about the fraction. The fraction is stored in the form also modified fraction equal to fraction minus 1. Very easy. So the value which is stored is a bit less than actual fraction. Also, we will see now why. For this we need an example. For example, let's consider the number minus 0, 0, or let it be just like this, minus 0.1 in decimal. And we need to store it in the machine representation. Okay. To do that, what we need is to calculate S, E, and F. And then we need to calculate, of course, modified E and modified F. Okay, we start from simplest, the S. Our number is negative, so S must be equal to what?
Minus 1.
Minus 1. This whole part must be equal to minus 1, but the S itself must be equal to what? Just 1.
1.
Just 1. Okay. Why? Because our number, let's call it X for shortness, because X is negative. Negative. So we need sign equal to 1 to make it negative. This part is easy. Second part is the exponent. To find out the exponent, we must express our number in the normalized form. So second step. So first step, we will define the sign. It is easy. Next, express our number x in exponent notation, and not just any exponent notation, in normalized exponent notation. We return what it is. We need to express it in such form. We need to find the power of 2 and a fraction that will give us, in this case, this number. Okay. For this, of course, we need to multiply this number by 2 until we get bigger than 1. Okay, so 0, 1, this is 1/10. If we multiply by 2, okay, we multiply by 2, what we get is 0.2. Next we have 0.4. Next we have 0.8. It's still not enough. And then we'll have 1.6. Right? That is, we started from this number, just multiplied by 2. We find out which exponent we should take so that the fraction will be as desired in the range between 1 and 2. Here it is. And we find the exponent that ensures fraction in range from 1 to 2. Among all possible representations, we found that one that have the fraction between 1 and 2. So, in the result, our x can be written as minus 1 power 1, as we have already done before. Next, there would be 2 power some exponent, and finally that there would be a fraction, and we now know that the fraction will be 1.6. Only this variant satisfies the normalization rule. Okay, so what is the exponent then? This whole number still must be equal to 0.1, so it must be it now calculates. If I put the power 1, this would be, let's see, a smaller number. If I put or a bigger number. If I put power 2, the number becomes even bigger. So the power must be negative. Okay, let me try minus 1. Minus 1, the result is... Oh, okay, so it's moving in the right direction, so in the backward direction, actually. We try minus 2, and we will see actually what we had before, and we have minus 3 finally, which will give us 0, 2, and finally minus 4 will give us minus 1, and that is what we searched for. We searched for the exponent and the fraction that combined by our formula give us our number x. So we found the exponential notation, the normalized one, for the number x. Actually, I showed you how it works in decimal, and we had to do the search. Yeah, we had manually choose the exponent. That is quite a long process, quite hard process. We can do this way more easily in binary, actually. So 2.1, we can do this in decimal, like we have done. First we try to multiply a number by 2 and find the power that gives us desirable range of fraction. And actually the power that we used, power 1, 2, 3, 4, negated will be the exponent. But there is a shorter path, which will be 2.2. Do the same in binary. For this we must, I mean that we need to convert our number to binary, and then look what it means for value to be normalized. Okay, let's see. Well, to do that it's easy to do it by drawing. I do it right here to the side. Our number was 0.1. We do not consider minus because it goes to the sign value. And in here we just remember how we converted fractional numbers to binary. We must remember that we convert whole part and fractional part in different ways. Here we have just the fractional part, so the process will be very easy by multiplying by 2. We do multiplying, we obtain first we obtain 0.5 or 0.2, I apologize, then 0.4, then 0.8, then 1.4.6, very careful on dot 6, and finally let's do it 2 more steps. Each time we take just the fractional parts, so it will be 1.2 and 0.4. Let's stop at this point. Our fractional part can be infinite, but of course we can store only finite number of digits in our representation. So the number of steps here depends on the allowed size of fraction. We cannot store more bits there. Okay, so in our example, we start from what our number is in binary. Our x is 0.0001110, and then actually the fractional part may continue, but we will use only the most significant digits. How many of them? It depends on the length of the fraction that you have in your number. Okay, so this is a presentation of x in binary. And now the question is, which power of 2 we must have for this number to be bigger than 1? Actually, every time we multiply by 2, this dot moves to here, to here, to here, or it can move to here. In this case, our number becomes greater than 2, but less greater than 1, but less than 2. Okay, so our decimal point must be put at this position. So our number must be like 1, 1, 0, and so on. Yeah, the decimal point is after the first one, multiplied by 2 power some value. And which value it is? Well, it is actually how many bits we must move the point to get the initial value. So we start counting from here and do counting. This is multiplying, actually dividing by 2. This is dividing by 4. This is dividing by 8. And this is dividing by 16. Or, in other words, 2 power 1, 2 power 2, 2 power 3, 2 power 4. Okay, so minus 4. Why minus? Because the value we should get is bigger than one we have started from. So, to obtain this one from this one, we must divide rather than multiply. Okay, and the difference between these two values is 4 positions. In binary, 4 positions are 2 power 4. Very easy, as we have discussed before. So, in binary, we do not need to search, to divide, and try to select proper exponent. Our exponent is always the distance of our decimal point from the position where it should be. Okay, so our number now is like this, in exponential form. What is E and F equal then? Well, that would be step 3, and the final step, calculate exponent and fraction in modified form. We start from exponent and fraction that we have here. The exponent here is minus 4. That is the one that stands in the power of 2. And the fraction is this, which doesn't have the power of 2. 1.10. In binary, we have already converted this one to binary. So I just note that it is already in binary. This one is not, but we should also convert them to binary. So I add here just the reminder for you. So we do all the following calculations in binary. So minus 4 in base 10 is minus 100 in binary. Okay. If you have difficulties to convert in your head, you can always use the division algorithm like we have done before. But to just use less time, I just gave the ready converted value to you. Okay, so now we have the exponent and the fraction in binary. But those are unbiased values. We must have biased values for which we should look at these formulas. For this we must know the E0 and the fraction. Nothing is very special about it. To calculate it is very easy. Let's see. The biased value for exponent would be this value plus bias. We will talk a bit later how to determine this bias, but for now let's let it remain as it is, plus E0. And the biased fraction would be this minus 1 as our formula says, and subtracting 1 from such a number is very easy. Here is the 1 that we must subtract, so the result will be 0, 0, 1, 0 base 2. Okay, that actually is almost the end. We have found the sign, the exponent and the fraction. We have found the biased exponent and the fraction. The last thing actually is this bias. It depends on the length of representation as well as the number of bits that we must calculate in our fraction. But to talk about that, we must take a break because we have used our break already.
Hello, Prof. We have this course material in the Microsoft Teams. Sorry, on the other.
On the other course?
No. This now we have this course material right in the system.
Yes, of course. You mean our you
No.
talk about our.
I'm talking about the lecture itself. You're going through like this process now. The last time I requested that you attach this in, you upload this so that I can have access to it. That was what I did. So I'm thinking this one also, if you could as well upload it so that we can always have access to this also.
Yes, I am gonna upload this one also.
Okay, thank you, sir.
Okay, for now, I just want you to work along with me, just to make it the simplest way possible. We started from this simple formula, and we needed a way to find the values of S, E, and F for any number. And actually, we are now almost ready. What one thing remains is just to talk about this offset or bias. But to do that, we'll take a break first. I do the pause in my recording for this time. Okay, so move on. And once again, what we have done, we have talked about this formula for exponential notation, which basically splits our number into 3 parts. Sign is apart from all other parts. Exponent and fraction represent the value of the number. The exponent is more for magnitude because changing exponent changes the magnitude very much. And the fraction is very limited in range, usually between 1 and 2. Why? Because between 1 and 2? Because when we change the exponent by 1, it is like multiplying or dividing our number by 2, because this is power of 2, right? If we divide or multiply any number from this range by 2, we will get beyond this range. This gives us a very easy way to define this normalized representation. Actually, if the fraction is in this range, the exponent must take just one precise value. Not many different values are possible. Okay. And when we have a certain number, of course, is the easiest ways to convert to binary and find the power of 2 that we need to multiply it by. so that the point will be after the first one. So the number will be between 1 and 2. Okay, and finally we said that the exponent and fraction are biased. Here is some unknown here bias, and here is it is just -1. So instead a number between 1 and 2, we obtain a number between 0 and 1, which will be easier to store. Actually, if before this -1 operation the number contained both whole and fractional parts, after we have removed this whole part, what remains is just fractional part. That is actually why this f is called fraction, because it stores only the fractional part. It has no whole part. Okay, and two questions remain, really. First of all, how many digits should we have in this fraction? We have done several when we calculated the binary representation, but maybe it's not enough, maybe it's too much, we don't know. And the second question is this bias for exponent. It also, as we said, it is chosen that any value for exponent with this bias will be positive. So, of course, it now must be greater than 4, but which exactly we don't know. It depends on which exponents are possible in our representation. So it must be greater than the maximal possible negative exponent. So the final step is actually the storage format, which will define both the length of fraction and this bias for exponent. So the storage format. How exactly this information about S, E, and F would be stored physically in memory. Okay, let's do it heading. And here, the storage format is basically very simple. As we said, as E and F biased values are stored in a single memory cell, or in a single register of processor and single memory cell. Let's have a, and this memory cell, of course, has fixed length, right? Of fixed length. Usually, the most used cases are 32 and 64 bits in modern computers. And let's have a picture, for example. Here is the picture that represents, that shows how our number can be stored in 32 bits in this case. As I want, but okay, let's put it here. Okay, so exactly. And here we have a memory cell of 32 bits. The bits are numbered from right hand side to the left hand side. So the highest bit will be number 31, the lowest will be 0. And our storage begins from the sign. It occupies the highest bit. The exponent in biased form is stored in following 8 bits, and the rest of 23 bits is for fraction. Okay, so this storage format has parameters that actually defines all the properties of storage. The parameters are actually the length, the total length, the length of exponent, and the length of fraction. So the length of exponent and the length of fraction. In our example, the length of exponent is 8, the length of fraction is 23, and plus we have 1 bit for sign. In total, it gives us 9 plus 23, 32 bits. Okay, so this is 32-bit floating point number. And a bit taking ourselves a step further, this particular representation is called single precision floating point, or in the programming language, in almost all programming languages, the type float or single precision will use 8 bits for exponent and 23 for fraction. For example, there is also the double type. Maybe you heard about such type already in programming, or in other words, double precision standard will have more. It will have 11 bits in exponent, and it will have 64 in total, which makes the fraction, the space for fraction be equal to 64 minus 11 and minus 1. 64 minus 11 minus 1, it would be 53. It seems 53, right? So 53 bits for, or 52 bits for fraction. Okay, these are two standards, and actually depending on how many bits you have in fraction and exponent, it will define both E0 and the number of bits in the fraction. So we may have the ending of our example. X is equal to 0 minus 0.1. We will store in the representation with I don't know, let it be 6 bits, or no, let it be 6 bits in exponent and 6 or let it be right like in the float, let it be 8 bits in exponent and 7 bits in fraction. This will make this will make 7 plus 8 plus 1, 7 plus 8 plus 1, 16 bits total. So our representation will occupy 2 bytes, exactly 2 bytes, of which 8 bits will be for exponent, 1 for sign, and remaining 7 for the fraction. Okay, and we will have a picture for this also. Let's have it from here. So it will be more easy to draw. Here it is. We have bits from 0 to 15, in total 16 of them. And we mark where are our parts in this number. The first bit is always the sign, yeah, the first one, and here is the division. Next 8 bits, 1, 2, 3, 4, 5, 6, 7, 8, up to here, will store the biased exponent, and the remaining 7 bits will store the biased fraction. Okay, now that is enough to answer the question that we have: what is E0 and what is the size of f? Now, the size of f is 7 bits, right? So, in our example, it means that the fraction must have 7 bits after the point. In our case, we have just 2 bits after the point, and these bits will be stored, of course, very straightforward, stored in here, 0 or 1, 0. Those are the bits that we have in the biased fraction, 1, 0. What to put in the rest of our bits, well, is quite unknown for now, because we haven't calculated the following digits. How could we calculate that? Well, of course, we could return to where we calculated the value of our number, and we can continue this process of multiplying like this and like this. For example, we have taken 2 more bits. They will be added here, 0, 1, right? And they will be added at here, like 0 and 1. And it is
Prof. So basically, in this case, that means we have limited length, right?
Right. That is what we started from. Yeah. We have the limited length representation, in which we must store all 3 parts. Yeah. And we decide, sooner or later, we must decide which part of this limited length will be used for each of 3 parts. Or actually for each of these 2 parts, because sign always is 1 bit. Okay. And when we decide how many bits is for exponent, how many bits is for fractional part, it defines the storage format. For example, A23, 1152 are the standards for float and double. But we can imagine any custom standard like this, as we use here. Okay. So, as soon as we decided on the size, we know that the fraction must have 7 bits after the decimal point. So after the first one, there should be 7 digits more. So we know now how long this process of converting must be. We must obtain 3 digits more. Okay, and what about exponent? In exponent, any value that we can store here should be positive. And it is this is ensured by the bias. So the first step that we take here is the length of fraction, and the bias E0 is always like 0, 1, 1, 1, 1, 1, and so on up till the end. E0 has the first bit 0 and all the rest bits equal to 1. And of course depends on the length of exponent. We should fill all bits with ones except the first one. Why? Because it is exactly the middle of the range of numbers that we can represent with all of this section of our number. It is half of the range. If we add this half of the range to any negative number, this negative number will move into the positive part of our range. So any possible exponent will be positive. In our example, we should calculate our exponent in biased form should be equal to minus 100, as we started from, in binary, plus 0, 1, 1, 1, 1, 1. In total we have 8 bits here, so we count 3, 4, 5, 6, 7, 8. Okay, this is the bias, this is the actual exponent, and we must do this adding up just usual adding of binary numbers, or actually subtracting binary numbers because one of them is negative. Okay, so we start from the big number which has 7 ones, 6, 7 ones and 0 at front, minus 1, 0, 0. Okay, we do it as usual. The last 2 bits are easy, 1 and 1. 1 minus 1 is 0, and the rest is unmodified. 1, 1, 1, 1, and 0. And as well as with integers, it's very important where the boundary of our length is, right? So it's very important how much of bits we have to the left, as well as it was with negative numbers in integers. So this is actually the final result that we have, and we should put it into a memory cell. The first bit is 0, 1, 1, 1, 1, 4 ones, 0, 1, and 1. And the sign bit, we have calculated it before. It should be 1 because our number was negative. That is actually the final result. I also will put the biased exponent here. It is 0, 4 ones, 0, 1, 1. Okay. So by using these simple operations like before, we now are able to calculate 3 parts, obtain the floating point representation. Actually, we now ready to give the ready algorithm for converting into floating point representation. Okay, converting into floating point normalized representation. There is a difference between normalized and denormalized. We are considering only the first case. And let's formulate the algorithm as it is. Actually, all the steps of this algorithm are done above, but well, for you to have it in the complete form, let's do it. So first we start from the value x. So first we convert given value x into binary using usual algorithm of conversion for fractional numbers. Into binary using algorithm for fractional numbers, which we have discussed before. For fractional numbers, you will obtain some zeros and ones and dot. It would be like in our case here. You will obtain some number with whole part and fractional part. It's not quite ready. You need to normalize it. You need to make sure that the point stands right after the first one in your number. Okay, so convert to normalized exponential form. Where dot will stand right after the first one, like here. Okay, and finally, when you are ready, you will have exponent and fraction, and you need to calculate the biased exponent and fractions using the length of storage format. This must be given to you to complete this step. That is why in all tasks, in all exercises, it is specified how many bits there is in exponent or in mantissa or fraction. Okay, and finally write down all three parts, that is sign, exponent and fraction, both biased into fixed length table, like we did here. And let's illustrate this algorithm once more with an example. In each step we will have a certain value. Let's have a value x equal to this time, no, let it be 7.5. Let it be like this. 7.5. Okay. What we need to do first, convert to binary. So, converting to binary is usual process. If we split this 7.5 into two parts, into the whole part and a fractional part, right? The whole part will give us 1, 1, 1 in binary. I will not do it complete steps, but you probably remember, you divide by 2 and you obtain the remainder 3 times. 0.5, well, you multiply by 5 and you obtain 0.1 in binary, and this fraction will not be infinite. Afterwards, all the fractional parts will be 0, so there will be no more digits. 1/2 is actually the simplest fractional value that you can represent in binary. That is why I have taken such number, because it's quite simple. Okay, so our number is then I'll put it ready, 111.1 in binary. Okay, now convert to normalized exponential form. Well, it sounds tricky, but actually it's quite easy. In normalized form, our number x should be expressed as some -1 power s, power s, multiplied by the 2 power some unknown exponent, multiplied by the normalized fraction. Normalized fraction should look exactly like this, only the point must stand after the first digit. So it should be like 1.31. Okay, the question is, which is the exponent? The exponent is multiplied by 2, so we just ask how many times we should multiply by 2 to get this number from this number. If we multiply by 2 just once, we obtain this. 2 times, we obtain this. Exactly what is needed. So exponent is equal to 2. Actually, exponent is just a difference of positions in which we have points, in normalized, in denormalized form. Okay, so in binary, to find exponent is really easy. Okay, now we write down actually what our exponent and fraction are. They are already before our eyes. The fraction is 1.111, and all the rest will be 0, 0, 0, 0, 0, right? Because in our number there are no more significant digits when we have converted it. Okay, how much of these digits should we have? It depends on the storage format. If we use the same format, then after the first one we should have 7 digits. So we count 1, 2, 3, 4, 5, 6, 7. So All the rest is not needed. And here also we must have 7. That would be like this. Okay, this is F, and E.
Or further.
It is.
Okay.
So for the exponent we have 2 power 2, but we need to express it in binary also, so it will be 1 0 in binary. So I just put here like this. Okay, and here also this number was already in binary, so I just mark it. Okay, and these are unbiased exponent and fraction. From those we should obtain biased exponential fraction. Okay, we return to our formula. Biased exponent is the exponent that we had plus the this bias, which is 0 and all ones. Okay, so in here we will have biased exponent equal to 1 0 plus 0 and 7 ones. Why 7 ones? Because exponent has 8 bits in total. Here we have 8 bits in total. Okay, adding up should be done by the usual algorithm of adding numbers. It will not calculate it for us, so we must do it. So we do what? We do 0, 7 ones. 5, 6, 7 plus 1 0. That will, in the last bit we have 1 plus 0 1. Here we have 10, so we have a carry. In here we also will have a carry, and in here also we'll have carry in all following bits up to this one. Here we have 10, carry, 1 plus 0 is 1. So, and actually this is the result of biased exponent 1, zeros, 6 of them, 1. And biased fraction is easier. We just subtract 1. We just remove this first whole part. That is what subtracting 1 is for. 0, 1, 1, 1. Actually, if we return a bit, we said biased fraction is fraction minus 1. Why? Well, if we have a fraction between 1 and 2, the first digit will always be same. It will always start from 1 and some extra fractional digits. When the first digit is known beforehand, there is no point in storing it. So what is stored is just the fractional part, or f minus 1. Okay. So we're ready to give the final answer. For this I use the table that I have here. In your case, on paper it will be much easier. You will just use cells on your paper. Okay, so here very carefully we draw the boundaries. Yeah, here is the sign, here is the place for the biased exponent, and it will have 8 bits, and here is the place for the mantissa or fraction f. Okay, the sign Okay, the number is positive, so sign is 0. The exponent, we have it, starts from 1. We have it right here. All bits equal to 0 except the last one. And the fraction, we put only the bits from the fractional part, and we remember all the rest are zeros, because our conversion ended at that point. I just skipped them. I shouldn't have done that. These bits are important. Well, it is same number as fraction here, but only without whole part. Okay, and that is the result. That is our number 7.5 in binary, in the floating point representation. And once more, looking at these two numbers that we have done, we can see one thing here. Looking at the exponent, at this first bit of exponent, it is here it is 0, here it is 1. Actually, where we have the first bit of exponent 0, we were dealing with the negative exponent. Where the first bit is 1, we are dealing with the positive exponent. This is because of the bias we have added. Actually, 0 exponent will look like this. Yeah, nothing will be added to this bias. If exponent is positive, we have at once the carry to this highest bit, so it becomes 1. It is actually the feature of all positive exponents. And if we subtract anything from this number, okay, the first bit will remain 0, and this is the feature of all negative exponents. Okay, so for exponent, the first bit actually gives us a kind of sign, but it is reversed, not like the sign bit here. Okay, so we can quickly see either this number is big or small. Okay.
This seems like it's finite, because if you continue, it's not going to end, from what I see here.
What about finite and limits? You see, we have a limited space here, so there are just a finite number of different numbers of different x's that we can encode.
But the computer can decide to increase this space and get more space from
yes.
This your explanation.
Yes, of course. If you have more space available, you are able to represent much bigger and much more precise numbers. But we'll talk about that. But one thing that you must understand is that, of course, in your real computer, you just have two options, 32 and 64. Of course, these 32 and 64 were not there for long. They were just starting from the end of 80s when our computers reached 32 bits. And of course, the size of numbers increases historically. But to make more bits in our representation, we must have a new architecture of a processor, because in all modern processors, registers have up to 64 bits. There are no bigger registers. So if some IBM or AMD companies will make a more complicated processor which will have 128 bits, okay, we then will use it.
Okay.
The mathematical part will work same. But the really tricky question, really interesting question remains: is this 32 and 64 really enough? What we can do and what we can't do with this length that we have? You see, what is real range and the real limitations now, and that we are going to discuss too. But first, we will discuss right now. The next step is precision and range. Actually, we got to this point.
Okay. Okay.
So, yeah. But before, of course, we will get to this precision and range. But before, the back algorithm. Actually, it's quite straightforward, but in your exercises, you will have the reverse task. You will be given with a number. For example, let's see, in this exercise, you have a number already in a floating point representation. Here we have sign, exponent, mantissa, or fraction, and you need to calculate which number it is. Let's have an example for that. For this, I'll also have some ready number, so that it will be clear, visible. So converting into floating point, and now we will have converting back from floating point to decimal. Okay, the reverse conversion. Okay, and we will have it as a next small topic. Actually, we must do all the steps in reverse. Right, we will have the final result, and we must calculate which number it is. Okay, we do that very similarly. The last step was write down all three parts. Okay, we just do it in reverse. We find all three parts in this representation. Of course, we need to know how many bits exponent and fraction occupy. Otherwise, we do not know which bits go where. Of course, yeah. So this must be specified in your task. For example, it will say the total length is 32 bits and the exponent is 8 bits. Well, this makes the fraction with 23 bits. Okay, now in this case the sign.
Excuse me. Can I interrupt you one moment? In the exponent, you put a 10. It's up. It's the before talk. You put a 10. That 10, that it's 2 actually. It is the exponent or it's the 2? It's the exponent, right?
Yeah, it is exponent because it was the power of 2.
Okay. So the power 2 is what you are putting like a 10 here, right? This is right. So if I have 5, 2 to power to the 5, I will have to put a 5 here in binary, obviously.
Yes.
Yes, right? Okay.
Yeah. Of course, this can depend. In the previous example, we had a number with negative exponent, -4. Of course, we had then 4 and minus, and we have subtracted it from the bias because it was negative. And of course, the value we obtained lesser value for the biased exponent.
Okay. Thank you.
And even more, once more, if in result we obtain the first bit 0, it means that the exponent is actually negative, because every time we subtract anything from this number, first bit is gonna remain 0. When we add anything to this number, if the exponent is positive, then we're gonna have a carry to this bit, and it will become 1, as we had in the second example, which will signify that exponent is positive. Okay. In this particular example, we know what the biased exponent is. It is shown in color here, but first it is sign. Sign is 0. It means that the value will be positive. The biased exponent, let's write it down. It is blue or cyan color. 0, 1, 1, 1, 1, 1, 0, 0. And you tell me now, is the exponent positive or negative?
It is.
It is more like this or more like this.
It's starting from 0, so it's obviously positive.
No, it doesn't. This is biased exponent. It doesn't start from 0. It starts from this bias. Yeah, it is added up to this bias. Mm-hmm. You see, if this number is clearly less than bias, right? So yeah, the exponent should be negative to obtain such number.
Okay.
If the first bit would be 1, so the exponent would be positive. So we already know that exponent is negative and not very high negative, quite a small negative number. But well, next fractional number. Actually, no, I'll do it as it is, but we can very easily get the fractional part itself without bias. But well, let's do it as it is. It is 0, 1, and all the rest is 0. So it is 0, 0, 0, 1. Yeah. We remember that only the fractional bits are stored here. So here they are. And then zeros, which are not needed for back conversion because they will change nothing. Okay, next step is the next step is calculate the unbiased exponent and fraction. Well, very easy. Calculate unbiased E and F. We know how those are obtained, so we can calculate back. E is biased exponent minus the bias, and the fraction is the biased fractional part plus 1. This is the easiest. That would be 1, 0, 1 in binary. We just add 1 that was removed when the number was stored. And in this case, we have our exponent in biased form. We subtract the bias, which is same as in previous example, because length is same. Yeah? In bias we'll always have 0 and all 1s. And we need to subtract. And very carefully we look. The first number is less than the second number. So for our algorithm of subtracting, of course, we need to reverse them. We need to do reverse. From a bigger number, subtract the lesser number, and of course negate the result. And this can be done by the algorithm like before, but well, I can put the ready solution for you, because you see all bits in this number are bigger than in this number, so there will be no carry. So from this bit 0 will be subtracted, so we obtain 1. From the previous bit 0 is subtracted, so we obtain 1. and all the rest bits are equal. So all the rest is 0, 0, 0, 0, 1, 1. And these trailing zeros are not significant, so our number is minus 1, 1 in binary. Okay, but okay, the next step, to get our value, actually we must have both exponent and fraction in decimal. Yeah? So convert to decimal. What we do is take minus e is minus 11 in decimal, and it is minus what? 2 plus 1, right? Minus 3. And the fraction is where it is this, and we convert it back to decimal. Fraction is always positive, so it is 1 plus 0 plus 1/4. Right? This is 1 by 2 power 0. This is 0 by 2 power minus 1. This is 1 by 2 power minus 2. Okay, so our number is 125. Okay, next, or rather it would be a bit shorter if we just add one more step before. Write down the exponential notation for the resulting number. Actually, we can convert to E and F first to decimal and then write down the exponential notation, or we can do those steps in reversed order, and this would be shorter. Why? We will see now. Exponential notation, we have it somewhere in here. In here. The sign of our value is 0. Exponent, we obtained it in binary, but really we see it is minus 3. And fraction is, I will for now write it down in binary. I have used the decimal value for exponents, so well, let me put it at the bottom then, so it will be just sequential. Actually, we may skip this step even. I will put it mark it as gray for this. Why? Because this multiplication is much more easier done in binary than in decimal. We can do it in decimal also, but well, in binary it's easier. Why? Because multiplying or dividing by 2 is just moving the decimal point in our number. Okay, so in our number 1, the point was here, and we should divide it by 2 3 times. Okay, the first time we have divided by 2, point has got here. Second time it is got here. Third time it is got here. Right, like here, like this. We had a number, and now we have 2 power 3 left. That means 3 positions. We have moved the number 3 positions to the right. It started from here, now it starts 1, 2, 3 positions to the right. And it is still in binary. There is a reason not to convert it to decimal before. Well, finally, we calculate the our number x in decimal, like positive number, from the binary representation. It will be rather 2 power minus 1 minus 2 minus 3 plus 2 power minus 4 minus 5, like this. We use usual algorithm for converting using powers of 2. Okay, and we can calculate what this number is like this, just using our calculator. And here environment does it for me. And of course we can compare in this particular case with the value that was known before. And we see that our value is a bit rounded. Yeah, we have here 3 instead of 25, but well, it's just the question of precision. Okay. So any number that is written in the floating point representation can be split into sign, exponent, and fraction, and these sign, exponent, fractions are in biased form, but they can be got back in the proper form, and then we just use the exponential form of our number, just substitute the exponent, the fraction, and these calculations are better done in binary. Finally, the final result is converted to decimal as before. Okay. Okay. And finally, for today, we're gonna discuss the precision range thing, which I have promised you. Let's have a small subtopic: precision and range. It is very closely connected to what we discussed before. Actually, the precision and range both are defined by the length properties. We have 2 length properties for exponent and for the fraction. And how exactly it is done, we will discuss now. Actually, what is the range? Range, we understand, is the big and the small, the biggest and the smallest value, right? So the range is the biggest and the smallest value that our floating point representation can represent. Yeah? Is the biggest and smallest values that can be represented given a certain length. Okay. The precision is the number of digits that are stored and not rounded. Precision is the number of digits that are stored and not rounded. It may be expressed in binary or in decimal. Binary or in decimal. But for all practical reasons, of course, we use precision and decimal. That would be the final result that we need here. And what about how many digits are stored and what is not rounded? Maybe in the previous example you have noticed our environment, which calculated this expression for me, have rounded the answer up to 4 digits after the point. That is why I haven't obtained 5 digits, and that is why the last digit is not quite same. Well, it actually rounds up everything that goes after it. That is rounding. And in the question is actually how many digits are actually trustworthy, because our fraction can be infinite, but only the first certain amount of digits are exact. All the rest are rounded. Okay, so we do now the rules for range and precision. Okay, the range is mostly defined by the exponent. Okay, is defined only, practically is only defined by exponent. Defined by exponent. Why? Because small changes in exponent change the value of our number very dramatically. Because if we change this value, number increases or decreases very much. And if we change the fraction, actually we can change only this fractional part. It doesn't have much influence on the total value. So it is defined by E. How exactly? In certain with certain precision, we can say that the range is from 2 minus 2 power minus maximal exponent up to 2 power plus maximal exponent, like this. Actually, the smallest possible number will have the smallest possible exponent. The highest number will have the maximal possible exponent, and the fraction will not be of any importance. Okay, and what is this maximal exponent? Maximal exponent is the maximal value that can be still stored in fixed length of bits, in the fixed length of exponent part of our number. How to define this maximal value? Well, very easy. Let's see in this particular example. We have 8 bits, right? So in these 8 bits, the maximal possible value that can be stored there is 111, 8 times 1. This is bigger value will give us an overflow. So this is the biggest, largest, this is the largest biased exponent that we can have. But well, this is biased. We must subtract the bias, which is 0, 1, 1, 1, 1, 1, 1, 1. And the result will be 1 and all zeros. So, to calculate the maximal exponent, we actually can do it very easy. Just it will always be the power of 2. Okay, so maximal exponent is 2 power the length of exponent minus 1. Because this here it is this number 2 power length of the 2 power 8 minus 1. Okay, and of course we should have an example right underneath. In here for precision we will have maybe 2 or 3 lines, and then an example. For example, the total length is 16 bits, as we had in our previous example. Okay, and I will have the picture for that, just to make an illustration. Let's have it from here. Okay. Total length is 16, and exponent length of exponent is 8 as before. We try to define the range. We will mark the boundaries here. This bit is reserved for sign. Here would be 8 bits for biased exponent as before, and those would be for fractions, for bits after the point. Okay. And the maximal exponent that we can store here is 2 power 8 minus 1. This number is nothing more, nothing less than this. 1, 0, 0, and so on, 0. We cannot store more because to this number we must add the bias. Yeah. So okay, and this number is quite close to the bias itself. Okay. This bias to comparison. So this exponent is maximal exponent is always 1, 0, 0, 0, and so on. And the value is such. And comparing it to the bias, which is 1, 0, and all ones, these two numbers are just different by 1. So the bias is this minus 1. You can just add 1 to this number and you obtain this number. Okay, so the maximal exponent and the bias are actually quite the same thing. Okay, and even more, this exponent is not cannot quite reach this maximal number. The maximal number is reserved for special cases. So we will modify our formula a bit. We will put here 2 power lengths of exponent -1 and -1. And it is equal actually to E0, to bias. So E maximal is such value, and in this case it is 127, and the bias is also 127. Okay, and here we mark that the exponent equal to all ones, as well as exponent equal to all zeros, are reserved, cannot be used for usual numbers, are reserved. This is will get quite important a bit later. For now, it doesn't make a big difference. It doesn't, it just changes our range by the factor of 2, but well, it will be way more important afterwards. Okay, so 2 values of these bits in exponent are reserved, namely the biggest and the smallest, which slightly narrows the range possible. So maximal value is this, and I would put it here. I would put it so the range is always from 2 power E0 minus E0 plus 1. The final result is like this: 2 power E0. Okay. In this particular case, E0 is 127, so we can have from 2 power minus to 126 up to 2 power 127. Actually, it's quite a big number. We can convert to decimal if we like. This is range in binary. And we can have the range in decimal. This would be the final answer. Range in decimal. Actually, we are dividing our powers approximately by 3.2, so that would be that would be 10 to power 37, more or less, approximately 2 power minus 10 power minus 37 to 10 power plus 37. We just used the logarithm of 10 base 2 to divide, to convert this number from exponent of 2 to the exponent of 10. So this simple short format, just 2 bytes, are enough to represent very huge numbers. To the 10 power 37, it is 1 and 37 zeros, huge number. And also very small numbers. 10 power minus 37 is 0 dot and 37 zeros afterwards, and then just 1. So the range is huge. But what about the precision? The precision is actually in this huge number how many digits are exact, and all the rest are rounded. So how many digits do we can trust in this number? And the precision is defined by the fraction. Very easy. The precision is a number of digits. So not only defined by the fraction, but is equal to the number of digits in the fraction, because those number of digits in the fraction and the precision are basically same thing. The length of this fractional part actually defines how much digits can you store. Only this works in binary, because we store their binary digits, right? And in decimal, is equal to the number of digits in fraction, but divided by 3.2, which is the logarithm of 10, to convert it to decimal. Okay, in our example, range precision in binary. Precision in binary is always the exact value, is exactly equal, because we know exactly how many binary digits we can store. But in decimal, this is approximate assessment, so we will have plus minus 1 digit. Precision in binary is what? 7 digits. 7 digits. So no matter how big or small my number becomes, only the first 7 digits are trustworthy. Okay. And what about decimal? So precision in decimal, where we have taken this 7 digits, it is a length of fraction. In decimal, we will have less digits. These bits contain fewer decimal digits. It would be 7 divided by 3.2, and it is approximately 7 divided by 3.2, and it is what? Well, not much more than 2. So it is approximately equal to 2 digits in decimal. So what is the implication of that? That although such format can represent very big numbers, very small and very big, but in those numbers only first 2 decimal digits are meaningful. For example, in this number, billion and 1. Is it billion? So like this: billion and one. In decimal. Or let it be billion and 5, just to make it look like decimal. Such number can be represented in our schema, but well, it's far less than 10 power 37. But what is the precision? Only the first two digits are meaningful, all the rest are rounded. So we don't know if it is a billion and 5, or it is a billion and 1,005, or it is a billion and million 5. All will be same, all will be rounded to the same number. Only the first two digits are meaningful, and all the rest are just random. They just randomly converted from binary, and well, we cannot use them. Okay, so that is the biggest application actually in practice. With floating point numbers, we cannot rely on all digits that we obtain. It is very common situation when we have, for example, I don't know, we have a huge number, for example, like billion. We add 1 to this number, and we quite often can obtain exactly same as before. Power 9. Why? Because this 1 is added to the part, to this part which is rounded, which is lost, where we store our number in the floating point representation. Only the first two digits will be stored in here. And that is why it's very crucial. And as soon as we talked about this precision and range, we will also talk about modern standards for data types. That would be the final thing for today, but is very closely related to ones that we had before, so we will cover it also. Okay, so the modern standards for data types. And here we have a small heading. And here also the modern standards for floating point types. The most important ones are float and double. Those that are used directly in programming. And so we must talk a bit more. What do they say about precision and the range? Now we have the framework, how exactly to calculate the precision and range of each of them. What we need to know, only the length of exponent and the length of the fraction, or the total length of representation. Okay, we will not do it by hand, although at home I encourage you, please try to take some float and or double. Look in the documentation of your programming language, which precision and range is specified there, and try to calculate it yourself and compare. And you will get some interesting results, ones that we are not quite discussed yet, but comparing will be quite interesting. I just will show you the excerpt from the documentation, which shows the final result. Here in this table we have the precision and range for all. Oh, it's not the one. It's not the integers. We need one about floating point. Let's find it somewhere. This is okay. Here it is, for example. This one will be fine. Let's consider this table, which shows single precision is float, double precision is double. Okay. Here is the actually form in bits that our number can take. This is the smallest number that we can represent. So the smallest, lowest boundary of our range, and this is the biggest one. Here we we see all that we have discussed. In the smallest number, the exponent is the lowest possible apart from all zeros. All zeros is the reserved value, so minimal exponent will be 0, 0, 0, 1. And this exponent will be minus 126, as we have calculated in our study here. This is exactly what we have done here. The range, as soon as our representation has 8 bits in exponent, we have the range from 2 to power minus 126 to 2 power 127. Actually, that is what we have here. The smallest number is 2 power minus 126. And it is approximately 10 power minus 38, 37, depending on the rounding. And the maximal number exponent is one shorter than the actually maximal value that can be represented here, because the maximal value is reserved. So instead of 128, we obtained 127. Okay, so it is a huge power of 10. Very similarly for the double precision. For the double precision, they didn't put here the value in bits because it will be quite long. But you will have the minimal and maximal power of 2, approximately 1000. And this will give you 10 to the power 300, approximately 3 times less. And this is the range that will suffice for any tasks that may arise in future even. So this double precision type is, at least speaking of range, it's far enough for any tasks. But this also only answers the question about range. What about precision? I can tell you that this floating point type has the precision of 7 approximately 7 decimal digits, and the double has 16 decimal digits. Okay, so let's sum it up. In float and in double, we have range and precision, right? So let's have here types. Here we have range, and here we have precision. Okay. So for the precision, for the range, here I copy the result that we had calculated. It holds for the float type, and in here it would be 308 and 308. Obtained in the same manner, only in a double type we have 11 bits in exponent. It makes far higher possible values. It is range. So it should be here. And in precision we have approximately 7 decimal digits. In this case, in double, we have approximately 16 decimal digits. Why approximately? Because one decimal digit is not exactly whole number of binary digits, so the last of these 16 digits will be rounded, and the last of these 7 digits will be rounded. Okay, and one more thing. This says nothing about digits after the point. There is no notion of after or before the point, so we cross it out. We put it like this. This is 7 digits in total, before or after the point. The position of point is not important. For example, if I have a float value, for example, in some program, I have a float variable equal to, I know, maybe dot 0.056, like this. A fractional number, yeah? Right? In binary representation, of course, it will be normalized. The exponent will be stored here, the fractional part here, and the precision is 7 digits. So only the 7, 1, 2, 3, 3, 4, 5, 6, 7. It seems up to here are gonna be stored. All the rest will be lost. So our efforts in calculating those digits were fruitless. Okay. What about double? In double, this number will be stored whole. All digits will be stored exactly because we have far more space available. Okay. Okay. And also, if then you will try in your program to calculate a minus, I don't know, the same value, you can obtain not 0 because of this rounding. When it is stored, it's not exactly equal to this number. Okay. Okay, and so it seems quite enough for today. Right now, let's have a second break, and then we will do 2 more examples from your home exercises. Let's have a 10-minute break. It means we will return here in 13:55. Okay?
Okay.
I'll stop the recording.